Mauri Betancourt, founder of Kelectrik. I'm a PhD in chemical engineering and a licensed professional engineer, and in 2023, I converted my 1974 Ford F100 pickup truck to be fully electric. I'll show you how I did it. Starting off at the outside, we have a typical J1772 charge port. These are used most commonly in North America. That charge port is directly connected to the charger. That charger takes the AC signal, converts it to DC, and distributes that voltage to the traction pack. That is controlled by the battery management system, which is here, that balances the battery pack to make sure that all the individual cells that comprise that battery pack maintain approximately the same charge when charging or discharging. Over here we have the DC to DC converter, whose purpose is similar to an alternator in an internal combustion vehicle. Its purpose is to keep the auxiliary low voltage battery, which is 12 volts, fully charged while the vehicle is in motion. It takes the full traction pack voltage, which is about 350 volts in this vehicle, and converts it to about 14 volts, which in turn powers all the small microelectronics used in this vehicle. Behind that are two components typical of any vehicle: windshield washer, fluid reservoir and pump, brake master cylinder, and vacuum booster, which is connected to a vacuum canister for extra vacuum. That canister is powered by a pump, which is located back here, which runs off of 12 volts and is used to keep the power brake booster vacuum. A pump like that's not usually necessary in an internal combustion vehicle because the engine will keep that vacuum. But since we don't have that capability in that belt system in an EV, we use a 12-volt pump to accomplish the same thing. Backing out just a little bit, we have a component that's common to internal combustion vehicles, which is a radiator. Now in front of that radiator is the fan and the condenser for the AC system, which I'll also show you momentarily. This large radiator came with the vehicle when I purchased it, and it's now used to cool the motor and the inverter using regular propylene glycol or ethylene glycol coolant. We have a smaller radiator here that came from a motorcycle that's attached to a coolant pump, and that's to keep the front battery pack cooled. We have a very similar setup for the rear battery pack under the chassis. On this side, we have the auxiliary battery. So this is the same battery I had when this vehicle was an internal combustion vehicle. It's a 12-volt battery. Behind that, we have a AC compressor, which came from a Nissan Leaf. Its voltage operating range is between 200 and 400 volts approximately. So unlike the AC compressor in an internal combustion vehicle, which is usually belt driven, this is driven by the full traction pack voltage. So in this truck, as I mentioned, is about 350 volts. This has a three-phase inverter inside of it, which takes that DC, converts it to three-phase AC to run the small motor that's inside this compressor, connected to typical AC system components like a dryer, AC hoses, and an evaporator inside, which I'll show you momentarily. So now the heart of the system. Up top, most prominent are most of the safety connectors and control system for the battery pack and for the inverter and motor. We have a high voltage positive bus, a high voltage negative bus. To those are connected the DC to DC converter, the AC compressor, and most importantly, the inverter. Followed by that, we have a fuse, safety contactor, safety switch, and a pre-charge circuit. The pre-charge circuit is essential. It prevents the capacitors in the inverter from charging too rapidly on startup. The last component up top here are the brains of the operation. They're both aftermarket devices. One of them is a battery management system that its main function is to balance the traction pack, and a vehicle control unit, which main function is to translate the throttle signal from the accelerator into a signal that the inverter can understand to propel the vehicle. Back here, we have the inverter, which came from a 2012 Nissan Leaf, and under that, we have the actual motor, which also came from the same Nissan Leaf, which you'll see momentarily under the vehicle. I forgot to mention we have a key switch bus, so these are all the components that come on when the key is turned. And finally, a custom microcontroller that I built and programmed to control the AC compressor. Here we are under the truck. We have in red and in light colored aluminum the adapter plates between the motor on the left and the original transmission on the right. I rebuilt the transmission, but it's the same 3-on-the-tree manual transmission from this model Ford F100. The 3 orange high voltage cables connect the inverter to the motor. Not visible from this view, but between the transmission and the motor is a coupler that on one end fits the spline pattern from the transmission and on the other end fits the spline pattern from the motor. This access port in the bell housing of the transmission shows the coupler between the transmission and the motor. This coupler was custom made. The transmission output shaft is connected to the vehicle's original drivetrain, which consists of 2 drive shafts connected via 3 universal joints, a hanger bearing, a differential, and then the axle. So this truck is a rear-wheel drive. So as mentioned earlier, 6 batteries in the front, 8 are in the back. There's a total of 14 batteries connected in series. Each battery module came from a Tesla Model S, and they were purchased from a junkyard. Down here you can see one side of the battery box, and this side shows the coolant hoses. The batteries are liquid cooled using a regular traditional coolant, in this case propylene glycol. This side of the battery box has the high voltage control box that has the battery management system satellite units that allow communication between the individual modules to make sure that they all balance relative to each other, as well as the high voltage negative and positive lines that connect to the front battery box. Over here we have the small radiator, also from a motorcycle, to cool the rear battery pack. Both the battery management system and the vehicle control unit can each be programmed using a computer and a USB. In this example, I have the battery management system connected to the computer via the USB, and you can see different kinds of statistics. You can program features, remove, edit features. So for example, if I want to show the thermistors, I can put the function SH for show, TH for thermistors, and it'll show the temperature read by 2 probes for each module for the 14 module, for a total of 28 probes. You can see that the average temperature is about 24 degrees Celsius, which is similar to the ambient temperature where I am. Another function is to show cells, which shows the voltage of each individual cell group in a module. These Tesla modules each have 6 cell groups. This gives a total of 84 cell groups for the 14 battery modules I have. You can see that the average voltage is somewhere around 3.63 volts. You may be surprised to see that the interior of the vehicle looks much the same as it did when it was running on an internal combustion engine. The general dashboard layout is the same, with this added control panel here. The features are an on-off switch for the pumps that power the coolant, that deliver coolant to the battery pack, a forward, neutral, and reverse switch for the motor, a state of charge gauge for the battery management system, an OBD2 port, which is mainly to read temperatures, currents, among other things for the inverter, current draw from the battery, battery temperature, and then inverter and motor temperatures. Over here, we have the controls for the AC system, the custom AC, and the evaporator. The accelerator is for an electric vehicle, so it throttles a voltage signal to the VCU. That's this one here. We have the brake, functions the same way. The old clutch is sitting behind the new electric clutch. The old clutch is not being used. The electric clutch temporarily puts the motor on neutral so that you can change gears if needed. Most driving, about 90% of the time, is done in second gear. If you need to accelerate quickly, you can switch into first. That's the gear changer there. And if you're on the expressway, you can switch into third gear for more efficient operation of the transmission. Let's take her for a ride. The truck drives smoothly in city streets and on the expressway. It's very quiet, and when needed you can change gears. I left the original transmission, which I rebuilt as part of this process. So the truck still has that vintage feel, but with new life breathed into it.